Hello everyone, welcome to Gate Pass, and in this video I am going to take problems that appeared in Gate 2014 and which were related to thermodynamics. So there were only 5 problems which appeared in this year and all of them were very simple. Okay, so let's see the first problem. Such type of problem also appeared in Gate 2018. Okay, so these type of problems, they frequently appear in Gate and they are very easy. Okay. So they have said identify the properties that are equal in both vapor and liquid phases at equilibrium. Okay. First one is density. Density is not equal. Temperature. For thermal equilibrium, the temperature should be equal in both the phases. So this is right. Chemical potential. Of course, for chemical equilibrium, your chemical potential should be equal in both the phases. Enthalpy, that is not same in both the phases. Okay, so it was a straightforward problem. So just tick the answer in which they said Q and R are correct. Okay, the next problem is question number 7, where they have asked you to match these quantities on the left hand side with these whatever the description they have given on the right hand side. So quickly let's see what matches with which of them. Okay, so del G by del Ni at constant temperature, pressure and number of moles of all the species J except I. Okay, immediately you know what is this. This is nothing but the definition of your chemical potential. So I am going to match this with chemical potential. So my P matches with 3. Okay, next let's see this option. Del G by del Ni at constant SV and Nj where J is not equal to I. Now the way it is written, it is incorrect, because if you had seen my first lecture in this series, I have told you that when you do a total Legendre transformation of U to G, okay, what you do is you convert S to the variable T and V to the variable P. Okay, so G is not a function of S and V. Basically, your U is a function of S and V, and when you do a Legendre transformation, then you get G, which is a function of T and P. So you cannot take a partial derivative of G with respect while keeping S and V constant. Okay, you have to keep T and P constant. So this does not make any sense, right? So it will not match with any of these. Now let's see option R. It is exponent of minus delta G0 upon RT. Okay, so this is nothing but your reaction equilibrium constant. So let's match R with 2. Okay, what else? S. What is this? And summation of all, summation over I, Ni d mu I at constant temperature and pressure, that is equal to 0. So you know that this is nothing but your Gibbs-Duhem equation. We have already seen it. So your S matches with 4. So your Q does not match with any of these, okay, but your P matches with chemical potential, R matches with reaction equilibrium constant, and S matches with the Gibbs-Duhem equation. Okay, keep in mind, if they had written something like this, that del U by del Ni at constant S, V and N is kept constant and J is kept constant where J is not equal to I, then this would have been equal to your chemical potential. Okay, over here this does not make any sense. So keep this in mind. So this is the next question, question number 6. It says that in a closed system you have an isentropic expansion of an ideal gas. You have to assume that it has constant specific heats, that is Cp and Cv are constant. Okay, and then you have to tell which of these curves represent this process. Okay, so first see, this is on PV diagram, this is on PV diagram, and option C and D, they are plotted as ln of P versus ln of V, so it's on log-log plot. Okay, now how to tackle this problem? See, this is an isentropic expansion, and that too for an ideal gas. So you can take this system as reversible adiabatic expansion. Okay, so for adiabatic process, you know that you can write PV raised to gamma is equal to constant. Okay, where gamma is your ratio of the specific heats. Okay, now if I take log of this equation, I can write ln of P plus gamma times ln of ln of V, that is equal to ln of C. Okay, so if I plot ln of P versus ln of V, okay, so first of all PV diagram, that is out of option. Okay, so what we have to see is option C and option D. Okay, now if I plot ln of P versus ln of V, okay, then I will have a slope of minus gamma. Okay, if I have a minus slope which is negative, then out of these two, this one should be correct. Okay, so your option D is correct. So it was a very straightforward problem. So the fourth question which I am going to take is that you have an ideal gas in a closed system and they have given you certain relations and asked you which one of them is correct. Okay, so first look at these equations. What you observe is that all of them are of the form PV is equal to nRT. PV is equal to nRT, right? So that's what you will observe, that for an ideal gas, what is it is showing you that all of these equations take the form of PV is equal to nRT. Okay, so that was just an observation, initial observation. Now let's see that they have taken partial derivative of U with respect to V and S and H with respect to P and S. So let's first write down the equations for U. So du, that is equal to TdS minus PdV, that is the equation which you remember. Okay, now I have told you how to write equations from this equation. So if I have dH, then how will I write it? Because H is obtained by the legendary transformation of V to P. Okay, so I will write TdS like that. Since what I will do is, I have told you the shortcut. So what you do is, if you are doing a legendary transformation and converting your variable V to P, what you do is change the sign and switch the variables. Okay, so this is the simplest way to remember all these equations. So I have dH is equal to TdS plus PdP. Now from these equations I will write down these partial derivatives. So first let's write down del U by del S at constant V, that is equal to T, del U by del V at constant S, that is equal to minus P. Okay, similarly your del H by del S at constant P, that is equal to T, and your del H by del P at constant S, that is equal to V. Okay, so I have written these equations. Now I will put one by one these partial derivatives and see which one is correct. Okay, so del U by del V at constant S, that is equal to minus P. So I will write minus P over here. Just to differentiate, I will mark a circle on it. Okay, del U by del S at constant V, that is equal to T. Okay. Now this equation takes the form minus PV is equal to nRT. So there is an extra negative sign, so this option is wrong. Okay, let's see this one. Minus del H by del P at constant S, it takes the form of V. Okay, what is del H by del S at constant P? That is equal to T. Okay, but there is a minus sign, so this equation again takes the form of minus PV is equal to nRT. There should be no minus sign, so this option is also wrong. Now what is this? Del U by del V at constant S, that is equal to minus P. Okay, and what is del H by del S at constant P? That is equal to T. Okay, so now this equation takes again the form of minus PV is equal to nRT. There is an extra negative sign, so this is again wrong. Okay, now let's see this. Del H by del P at constant S, that is equal to V. So this is V. Del U by del S at constant V, that is equal to T. Okay, so this equation takes the form PV is equal to nRT. So option D is correct. Okay, so there were only two steps. Look at the equations, see that they are of the form PV is equal to nRT. Then second step will be identify which variable has been used. So you are using U and H. So I wrote down the two equations for it. Then from these equations I found out the partial derivatives which appeared in these equations and then cross check which one was right. Okay, now let's move on to the last problem which appeared in 2014. So the last question which I am going to take is based on vapor-liquid equilibrium. So you have a binary liquid mixture which is in equilibrium with its vapor at 25 degrees centigrade. They have given you certain data set. They have given you Einstein's equation, and just make sure you check the form of the Einstein's equation, because here it is log to the base 10. Pressure is given in torr and temperature is in degrees centigrade. So do not make a mistake of converting it now to 298. Okay, use 25 here. Fine. Further, they have said that your vapor phase, it behaves as an ideal gas, and your liquid phase non-ideality, it is defined by these relations of activity coefficient as a function of your mole fractions. Okay. Now they have given you x1 which is equal to 0.11, and they have asked you to find out what is y1, that is the mole fraction of component 1 in the vapor phase. So I have told you these questions, they are solved using Raoult's law. So first of all we will write Raoult's law for both the components. Okay. So I am going to write my y1p, that is equal to x1 gamma 1 p1 saturation. Similarly, I can write y2p, that is equal to x2 gamma 2 p2 saturation. Okay. Now in order to find y1, I am going to use this equation. Let's see what quantities we know in this equation. So y1 we have to calculate. Total pressure is not given. x1 is given, gamma 1 I can calculate using this equation, because x1 is given and x2 is nothing but 1 minus x1. Okay. P1 saturation, that is the saturation pressure of component 1. I can use Einstein's equation and calculate that. Okay. So gamma 1 and P1 saturation can be calculated. First of all, the first step in this equation, in this question, is to calculate your total pressure. How do we do it? We just add these two equations, and when you add them, what you get is y1 plus y2p, y1 plus y2 times p, that is equal to x1 gamma 1 p1 saturation plus x2 gamma 2 p2 saturation. Okay. Since y1 and it's a binary mixture, and your y1 plus y2 should be equal to 1, so I can take this as 1. So your total pressure is equal to this quantity. Okay. So now we will quickly calculate what is our P1 saturation, P2 saturation, what is gamma 1, what is gamma 2. Then we will find total pressure. Once we have calculated total pressure, then we will calculate y1. Okay. So I have calculated that for you, and you can check my answer. If it doesn't tell you, then you can write to me in the comment section. Okay. So P1 saturation, if I calculate, okay, keeping all these units in mind, then my P1 saturation is 179.846 torr. Okay. Calculate your P2 saturation, that is equal to 43.36 torr. Okay. Now use this equation. Calculate gamma 1, keeping x1 equal to 0.11 and x2 is equal to 0.89, and what you get gamma 1 as 4.627. Similarly, use this equation of ln gamma 2 and then calculate your gamma 2. It comes out to be 1.0274. Okay. Now I am going to plug all these values in this equation and calculate pressure for you. So that pressure, it comes out to be 131.18 torr. Now your question is very simple. Y1, that will be equal to, x1 is nothing but 0.11, multiply with gamma 1, that is 4.627, multiplied with saturation pressure of component 1, 179.846, and divided by total pressure, which comes out to be 131.18. Okay. Do this calculation and you will get the value of y1 as 0.697, or I can round it off to 0.7. So this is your answer. Okay. You have seen that this is a very simple problem. You have to use just Raoult's law and you can solve this problem. The only place where you can do a mistake is while calculating your saturation pressures. In a hurry, you can forget that the temperature is given in degree centigrade, okay, or your this is not your log to the Neperian base, it is log to the base 10, okay. So here is where you can make a mistake, otherwise it's a very straightforward problem. Okay, so I hope you like my teaching, and if you like this video, please don't forget to subscribe to my channel and like this video as well, and thanks for watching.